How can multicollinearity be diagnosed? Well, the old-fashioned way is to create a bivariate correlation matrix, and this is the way that I was initially taught to do it for all of your independent variables. So the correlation matrix will show us bivariate correlations among all of our independent variables. So we can check this to see if there are high correlations between any of our independent variables. That will show up on our correlation matrix. The problem with this is that we'll only do it for 2 variables at a time. So if you're dealing with multicollinearity, where you have 3 or more variables that are correlated with each other, that's not going to show up as well. We may not be able to diagnose that just with a bivariate correlation matrix. Allison suggests another option, which is to regress each independent variable on all of the other independent variables to look for high R-squared values in any of those regressions. And I'm sorry, that should be R-squared, that R2. Raise that up a little bit. So it should be R-squared. We should be looking for high R-squared values in any of those regressions. And he recommends using a 0.6 threshold for determining when we have near extreme multicollinearity. So if we regress each independent variable on each other, so using one of them as a dependent and the other as an independent, and we see high R-squared values in those bivariate regressions, that's a sign that there's a problem, that there's a correlation between those 2 variables. Last week, we included multicollinearity diagnostics when we were doing our SPSS examples, and those give us tolerance measures that we can use to assess multicollinearity or to diagnose it. We saw in our SPSS output last week that there were 2 values given to you in the multicollinearity diagnostics. The first was a tolerance value, and that ranged from 0 to 1. And so that was measured as 1 minus the R-squared value for that regression, for that little partial regression that it did. And so that was low tolerance scores connect to high multicollinearity. So if your R-squared is really big, your 1 minus R-squared is going to be really small, and that's going to tell you that there's a multicollinearity problem. So we are given both the tolerance measure, and we're also given the variance inflation factor, or the VIF. And last week we talked about how we want tolerances to be big and VIFs to be small, right? Because the bigger the tolerance measure, that's the smaller your R-squared, that's the smaller the regression coefficient between those 2 variables. So we want our tolerance values to be closer to 1, but we want our VIF values to be small. And how small, we talked last time about using thresholds like 0 to 5 typically represents low multicollinearity, 5 to 10 represents moderate multicollinearity, and then larger than 10 tells you that you have near extreme or extreme multicollinearity. So those are the guidelines that we can use, and the SPSS run can be very helpful in detecting it when you may not be able to visually see it, or you may not be able to tell it just from looking at a correlation matrix. Allison talks about blue measures, and when you see in statistics this the blue, that term, we're talking about best linear unbiased estimates. So we are looking for regression models that meet the assumptions that we've talked about the last couple of weeks. And those that meet those assumptions are called blue estimates. They are the best linear unbiased estimates. What's important to know about multicollinearity is that it is not a violation of any of those regression assumptions. So it doesn't violate any of our regression assumptions. What it does, though, is it gives us an inflated standard error value. And how big? So the standard error of the coefficient is likely to be very large when we have multicollinearity. How big? We can actually kind of get a sense of how much inflation there is in the standard error by taking the square root of the VIF. So if the VIF is the variance inflation factor, what's the square root of variance? The standard deviation. And we know that that relationship between standard deviation and standard error, we know what that is. So if we have a VIF of 9, which is pretty darn high, then the square root of 9 is 3, right? So we can interpret that to say that our standard error is 3 times larger than it would have been if that variable were unrelated to the other independent variables. So we can use that variance inflation factor as a measure of just how affected our model is by collinearity present in our variables in our equation. Some more of the consequences of multicollinearity. The big problem is that it becomes really hard to find statistically significant coefficients. This shouldn't be surprising, right? The larger the standard error, the harder it is to find a statistically significant coefficient. So it creates that problem. One way to deal with this is to delete those variables from the model. But in removing the impact of that collinear variable, or one of those variables, maybe one of them, not all of them, will improve our coefficients explanations, and it often reveals the magnitude of the relationship between the other independent variable and in the model and the dependent variable. So if our model improves by pulling a variable out, and that probably means that there was some sort of multicollinearity between that variable and another independent variable already in the model. When independent variables are highly correlated, we see what's called a tipping effect, where small differences in the bivariate relationships with the dependent variable get magnified into really large differences in the regression coefficients. Sort of overall, multicollinearity produces instability in our regression coefficients. It makes multiple regression a lot more sensitive to minor errors, and therefore makes the coefficients from that regression less robust.